What I'm going to do is I'm just going to give a couple of kind of really basic beginning lectures on dynamics. And here are some of the references that I've been using. I found some really cool lecture notes that were from some class in England that were on there. So that explains a lot of topics really well. A lot of the more classical books, like by Brennan Stuck, I use Intro to Dynamical Systems. There's kind of an older book by Clark Robinson that discusses stability, symbolic dynamics, and chaos. And then a really good book that I've been using a lot is the last one, The Introduction to Symbolic Dynamics and Coding. That actually treats regular dynamics and talks about that kind of in a really broad sense as well. And it does a really good job of doing that. So really what I'm going to do today is kind of talk about some basics, go over a little bit of topology, go over a little bit of metrics-based stuff, and then we're going to kind of jump into some basics things with dynamics. Okay, so first of all, whenever people ask me what I study and I answer with dynamical systems, kind of an immediate follow-up question that I tend to get is, well, what is it? What is dynamical systems? And how would you explain it? So simply put, we just think of dynamical systems as just the study of long-term behavior of evolving systems. So you have some kind of system that's evolving, and we want to know kind of what goes on in the long term. Okay, so a lot of things that you've seen maybe in ODE can all be described by this. So you can think of taking an investment and it's compounded over some kind of time. It could be continuous, it could be monthly, it doesn't matter. That would be a dynamical system. Your predator-prey models would also be considered dynamical systems. If you have some kind of evolution of some kind of maybe disease through any type of population, that would also be an example of a dynamical system. So a lot of these continuous time systems, though, that we deal with really can be described a lot by just an ODE, or a differential equation. So that has a very close link with ODEs, of course. Okay, so, and do keep in mind, too, a lot of physical systems can be completely determined just by taking a finite amount of measurements. So for one, if you have a swinging pendulum, for instance, you can completely determine it just by its angle from the vertical and then its angular velocity. So you can completely determine it just by these things. Or if you have a gas, then you can completely determine it just by giving the position and the momentum of each molecule. So whenever we have a dynamical system, well, as time goes on, then these values are going to change. So what you can kind of think of, if you want to intuitive sense of what's going on here, is that we'll let m be the set of all possible values. For our particular system. Okay, so what you can kind of think is that, well, if you have your set of all possible values, kind of imagine that you're filming a movie, and you have per frame kind of represents what kind of change is going on as far as the dynamical system is describing. Okay, so as the system evolves, we're going to assume that the laws governing the change from each kind of frame from one second to the other don't change as far as time is concerned. Okay, so this dependence or this change usually leads to a function. Okay, so to describe the thing that's going to describe our change is we'll usually have a function phi that'll go from our space of all possible values to right back into our space, and we usually assume it to be continuous. Okay, so this thing is usually going to be continuous. So the way that you can think about a dynamical system, well, if you start off with x and m, this is just the initial state of the dynamical system. Okay, so this is just kind of like an initial condition, if you want to think of it like this. Okay, and then, again, kind of thinking of it as like a movie, then in the next frame, what you would have is that your system would act on that thing, and you would get something right back in m. So this would really, if you want to think about it in terms of like time or anything, this would describe your system with this initial condition at kind of your t equal to 1 case. And then you can keep going and evolve it even further. So the phi squared notation is just applying phi to the phi of x, and then we'll get the same thing but it would just be at t equal 2. Okay, so what we're interested in is what happens as we keep going on and on, as we go further and further into the system. So really the dynamics here, kind of in a simple sense, really just boils down to it really just comes down to studying the iterates of a certain point in your space under this map. Okay, so it's really just, it comes down to just studying iterates. Okay, x, we have phi of x, the square root of x, and so on and so forth. And see how those points act. Are those points periodic? Are they coming back on themselves? Are they going back to the beginning? Are those points eventually going to be periodic? Are they converging to some, maybe, are they converging maybe to some fixed point or some point in the space? What's going on with those dynamics? Okay, so at the heart of it, this is really what we're going to kind of be talking about, and how certain dynamics can really affect how these iterates will look. Okay, so before we do any of that, since the map is, we're assuming the map to be continuous in this case, I will talk about a little bit of topology because in this beginning lecture, I'm just going to talk about the basic dynamics, but really in the next time, I would like to talk a little bit about symbolic dynamics. And we're going to use kind of a couple of topological notions in order to describe our system. Okay, so, and one of those things is, of course, continuity. Okay, so the first thing we're going to do, just in case you need a refresher on some topology, is we'll do just the topology review. Okay, so right at the beginning of it, before you can talk about continuity, you really need to know kind of what's the topology on your space, because that's what determines the continuity in this case. So what we're going to start off with is just a definition of topology. Okay, so what we're going to do is we're just going to let X be a set, and we're going to assume it to be non-empty. So in topology, I'll just denote it with the T and the squiggly thing above it. Okay. So a topology T on X is just a collection of sets such that you just have three conditions at hold. So the first condition is that the empty set and X are in the collection T. The second condition is that if you have a collection, and this collection can be countable, uncountable, it doesn't matter. Okay, so any collection that you have of sets such that each U alpha is in that collection T, then the union of all of them have to fall back in it as well. So if you union all of these elements over alpha, then this is also going to be in the topology as well. So you can just think about this as the topology is closed under any union of any open sets. And then number 3, a similar condition with the intersection, but you're only allowed finite intersections in this case. So if you have a finite collection of sets such that each UI is in your topology for each I between 1 and n, then that intersection is going to be in there too. So a topology is just anything where the empty set and the X are always going to be in there, so it's kind of the basic thing that you need for all topologies. Any number of union of elements that are in the topology is going to fall back in there, and any finite intersections are going to be in there as well. Okay, so just some basic stuff for that. So using this definition, okay, we'll just say a set U that's actually in this collection, we call an open set. So it's kind of the generalization of what an open set is. So we'll call this an open set. And in kind of in opposite to the open set, you can define a closed set as well. So since we have a notion of open sets, you can define closed sets, and closed sets are just going to be complements of open sets. Okay, so that is, what we'll have is that closed set that's contained in X is just simply the complement of an open set. Okay, so that is C is equal to X, take away U for some open set in your topology. All right, so this is just the basic definition of a topology. Very, very general definitions to deal with. We can think kind of like what do the open sets look like and how can we really generate them? And this is where the notion of a basis comes from. You can think basis kind of like in the vector space sense as well. So let's talk about basis really quickly as well. Basis, B for a topology, T on X, is a collection of sets such that just two conditions go for this. So the collection B actually covers X. So if you union all the elements in B, you'd actually get X back. Okay, so it's going to cover everything in X. And then if you take two basis elements, so if you take B1 and B2 that are in B, and we just assume that their intersection is non-empty, then for all X in the intersection, there actually exists a third basis element, B3, such that X is going to be contained in that basis element, and we can fit that basis element inside of the intersection. Okay, so it's kind of like if you intersect any two basis elements, you can find a third one that sits inside of there. That'll contain your point X. All right, so this really kind of will give us, if you're a little bit fuzzy on the topology, this kind of works really nicely in kind of what happens with our open sets and what's really going to describe our open sets. Okay, so for one thing, this collection B it can be uncountable. Oh yeah, go ahead, Mo.
When you say cover, is it a subset of that?
Yeah, you can be equal. It's fine. Yeah, it would be equal. All right, so a basis, like I said, it can be uncountable. It could be anything. The cardinality of that collection can really be anything. But if B is a countable collection, then X is said to be a second countable space. So in case I use the notion of second countable or anything, whenever we go into the symbolic part, that's all that second countable means. It just means that your basis is a countable collection. Right, so good deal. So the basis that we have here, kind of what's the intuitive, where's the basis going to really come in and helping with our topology? Okay, so here's a way that you can think about your basis. Okay, this is really what basis is doing. Okay? It kind of does what a basis in a vector space does. It really generates all of your elements. In this case, our elements that we're considering is really our topology, our open sets. So the basis really just generates all of the open sets here. So a basis is just going to generate all open sets. Okay, and what I mean by that is that for all, or for any open set U in your topology, then for each x and u, there exists a basis element b such that x is actually contained in that basis element, which you can put inside of u. Okay, so you can always find a basis element that will contain any element that you want that sits inside of u. So you can really think that you can do this for every x and u. So really you can just write u as a union of basis elements. That's really all that we're saying right here. And so the basis is really the building blocks of all of our sets, all of the open sets. All right, now the different type of topologies that we're going to kind of deal with, at least in this setting, are going to be called, we're going to use the discrete topology and the product topology. These are the two that we're going to use, especially in the symbolic case. So we're going to let x be a set. Okay. If we just let our topology T be equal to the entire power set of x, so any subset is thrown into your topology, then we say that x has the discrete topology. And in the discrete topology, since you're allowing every set to be open, well, every set is going to be open and every set is going to also be closed because of this. Okay, so in the discrete topology, every single set is open and closed. Okay, so that's kind of the biggest topology that you can possibly have. Okay, so all your collections are always going to come from the power set, but if you just let the entire power set be that, then that'll be the discrete topology, and that's the biggest that you can do. The other type of topology is the product topology. Okay, so I'm going to define the product topology just in general. So we're going to let x, we're going to let xi just be a collection of topological spaces. Can be uncountable, it doesn't matter. We're just going to let this be a collection of topological spaces. And we're just going to let capital X just be the Cartesian product of all of them. So we're going to let X just be the complete product of all of those all together. Okay? So we're going to define the product topology. On X as follows. So what I'm going to do, I'm just going to describe what an open set in this thing looks like. Okay, so an open set is unions this would say an open set is unions of sets of the form we're going to take product of sets UI, where each set UI is actually open in the corresponding topological space Xi. Okay, so such that UI containing Xi is open. And then there's this other condition that we put on here, and this is really for a later theorem that I'm going to refer to called Tikhonov's theorem. So we have that each UI is going to be open in its corresponding space Xi, and we'll have that UI is actually going to be equal to the entire space Xi that it comes from for all except for finitely many indices. So you're allowed your UIs, you're allowed to have at most finite amount of them not be the whole space that it's corresponding to. And so UI is going to be equal to Xi for all but finitely many. Indices I and I. So this is called the product topology. If you drop this condition just for just for your information. If you drop the condition UI equal to xi, that does define another topology. It's called the box topology. Okay. And this is really going to be, I'm going to refer to this whenever I go over a theorem by Tikhonov, and what happens whenever you take a product of compact spaces, and why this definition is kind of needed.
I have a question.
Yeah, sure.
How do you connect the topology to the algebras, like sigma algebra? How do you connect those two?
Well, they, I'm not sure.
The
I'm not sure
sigma
what you mean.
algebra code, it's the countable intersections. This is finite intersections.
I mean, if you can, you can compare the two, right? They kind of look the same.
Okay.
They have kind of the same. They have kind of the same idea. They kind of all work the same too. I mean, for a sigma algebra, you can really define whatever you want, right? As long as it satisfies the axioms for topology, right? And the topology kind of is the same thing, but you just have to be careful because in a sigma algebra, you're closed under complements and unions, right? But you don't get, like, in the topology, you're only closed under finite intersections, right? And you're not going to be closed under complements, right? Because if you take, unless you're in the discrete topology at least.
Yeah, the discrete topology and the sigma algebra, because even when I look at the product topology,
right.
I know that you have, not a sigma algebra, but I know you have not an algebra or a semi-algebra where you have this type of property.
Mm-hmm.
So I'm like, okay, is it the same terminology, but I mean different areas, or is
it's related. It's not. They're definitely a little bit related to each other. I wouldn't say that they're the same though. And this is just like, I guess, what I see right there. So I would imagine that maybe in some cases you can define a topology that will maybe coincide with your sigma algebra as well, but in general they're going to be different. Right? Because I mean, you can just, as long as you satisfy the axiom, you can put whatever topology you want. It doesn't have to play with the sigma algebra at all.
Okay.
Are there any other questions? So, all right, so why did we kind of build up all this topology a little bit? So the only thing I really want to refer to the topology for is just for continuity. Because the continuity, from a dynamical systems kind of point of view, the map that governs the change in everything is going to be a continuous map. So if you change the topology, you change the map, which means you're changing the dynamics. So everything is kind of very delicate whenever you start playing around with the continuity and you start playing around with the topology on a space. Let me just remind you of the continuity in just this general sense. So we're just going to let x t1 and y t2 just be two topological spaces. So we say a map f that goes from x to y is continuous if for all u contained in y that are open, so for all open sets in y, if you take their preimage, they're going to be open in x. So for all open u in y, then the preimage of u is actually going to be open in x as well. Okay, so this is really just a generalized definition of continuity. If you have a metric space structure, this is the equivalent to your epsilon delta definition of continuity as well. If this map F, if F is 1 to 1, if onto continuous with a continuous inverse, then we just call F a homeomorphism. All right, so I use the term homeomorphism a few times. I'll definitely use the word continuity a little bit. Okay? But as far as topology is concerned, this is all I really wanted to cover as far as topology is as far as what we're going to use really in the topology sense. So are there any questions on anything? Okay, so if you want to kind of have like an example in your head, maybe with the topology, you can always think R, where you have the usual topology. Your open sets in that case, your basis would just be open intervals. So that would generate all your open sets. So all your open sets just look like unions of intervals. Okay, so you can always have that in the back of your mind. All right, so I'll cover a little bit of metric space and then we'll jump into the dynamics. So let me cover a little bit of just some things from metric spaces. This will really just cover a lot of just sequences and stuff like that, since we're studying in dynamics really the behavior of these iterates and what that sequence kind of looks like. We kind of need to know what the convergence is in those sequences. Okay, so that's what we're going to deal with. So let me just redefine for you metric space. Just give you a refresher on it. So a metric space M comma D just consists of a non-empty set M and a distance function or a metric and this distance function D is just going to go from M cross M into non-negative reals such that for all x and y, the distance from x to y being equal to 0, if and only if x equals y. If you switch the order, distance from x to y is just going to be equal to distance from y to x. And the distance from x to z is going to be less than the distance from x to y plus the distance from y to z, or the triangle equal.
The dot that always greater than equals 0.
What's that? I'm sorry?
The dot just
Other two.
x
Yeah.
y. Oh,
It's already covered. It's all good. All right. So yeah, we already have that covered. So and this will cover the only case where it's 0. All right. So and then other than that, it'll just be positive strictly. Okay. So if you're thinking kind of in the topological sense, okay, just of the stuff that I covered before, right? So this is really the metric space is a topological space in its own right. Okay. So you can just think of this as that open sets in a metric space. They're generated, are really the basis for it. They're generated by open balls. So I'll use this notation for it. So the ball of radius r centered at x is just a set of all y and m such that the distance from x to y is less than r. Okay, so that really gives you a basis for your topology on the metric space. So all your open sets look like this, okay, if you want to think about it in a topological way. So just one thing that's really important, that's kind of subtle, is that the open sets in your metric space are generated by open balls, which is dependent on your metric. So again, those open sets are being affected by the metric. The open sets affect continuity, and all of this stuff is affecting your topology. So if you change your metric on a particular system, whenever you're talking about dynamics, you're changing everything, really at the same time. So you have a really profound change on things whenever you just mess with one thing. Again, very sensitive things in dynamics. Okay, so let's just take some examples. And what I'm going to do, and I'm going to take some examples that I'm going to tend to work with in dynamics. So one, I'm going to do a lot of my work on the circle. And I'm going to...
Does that still hold if they're uniformly equivalent metrics?
Say that again?
if the uniformly equivalent metrics have metric spaces, most of the rules still hold between each other.
Well, if you have metrics that are equivalent, then their topologies are the same, right? So if you happen to change the metric, I don't want to do too much of the topology that goes with it, but yeah, if you change the metric but you end up getting like an equivalent type metric, that means that your topology is really not changing. So the continuity won't change in that case. So in a dynamical sense, you're really not doing anything. Maybe in the dynamical sense that may translate into like maybe rescaling. It may measure the distances a little bit differently, but it's really not affecting the dynamics. Like it's not going to kill periodic points or anything like that. Okay, so what I want to do is I want to take some examples of some metric space that we're going to deal with. And I'm going to present them kind of maybe in a way that you're not maybe used to seeing them. So the first one I'm going to do is that what we're going to do is we're going to start with the unit interval. And what we're going to do is we're going to start with the unit interval 0, 1, and we're going to glue together I'm going to put the quotes around that because I'm not going to really mathematically define what it means to glue together as far as topology is concerned, but we're going to glue together the points 0 and 1. Okay, by doing this, what we're going to do is we're just going to, you can kind of visually see what's going to happen, we're just going to create a circle, right? So we're just taking the unit interval at 0 and 1, and we're going to bend it around. We'll eventually just get that. That's all we're doing. Right? So we're just taking the endpoints and then gluing them together. Okay? So this is kind of like what we're going to be doing as far as like viewing the unit circle. You don't have to start off with the entire interval 0 to 1. You can actually just start off with a half open one. Okay? So we can just start off with, so just let's let n be equal to 0 and 1 and do the same identification. The reason why we don't need 1 is because we're really, by gluing together the points, we're really calling the point 0 and 1 the same thing. So we're kind of identifying them together, just like you would in a circle. Right? So if this was kind of like your 0, you go around the circle, you end up right back there. You can kind of think about that. Those things are being identified together. Okay, so we're just identifying all that together, and what we're going to do is we're going to define a metric on this. The distance between x and y is just going to be the minimum of these three values. So from x minus y, 1 minus x plus y, we'll define this metric on the kind of this new way to kind of view the unit circle. Okay, so we'll have this metric here. So the way that you can kind of view this metric is that this distance function, all it does is it just measures, by taking the minimum here, it just measures the shortest arc. Between x and y. Okay, so with this metric that we have here and this identification of 0, 1, this is how we're going to view the unit circle in a dynamic sense. Okay, so this is just the unit circle. So this is how we're going to view the unit circle. So like I said, a lot of the examples I'm going to do are really going to be dealing with the unit circle. You can get actually a lot of mileage out of examples from the unit circle if you want to describe some dynamics in our particular study. All right, so the other example that I'll be dealing with is just the torus. Okay, so we're going to let S1. I'm going to denote it with the S1 now for the unit circle. Okay, so I'm going to let S1 and I'm going to view it like this with just the endpoints identified. So we're going to view that unit circle like this again. And then we're just going to let, I'll use this notation for this. You'll see it maybe differently in other books, but I'll do kind of the double bar T, and I'm going to take the product, S1 cross S1. Okay, so this will be, if you want to visualize, this will kind of look like your donut. Okay? And then we can put a metric on this thing as well that's related to the metric that we have with S1. So we can put the metric we're going to take kind of a cross of the two metrics together. So if you want a cross of the two metrics together, you can really do this with any metric, any two metrics that you want, but here we're taking D to be the same in both cases. So like this, and then this is just defined to be the max of the distance from X to Z, and then the distance from Y to W. Okay, so we're just taking the maximum of the distance between the X coordinates and the distance of the Y coordinates. And that D is still the same one that we used in this case. Okay, so that's all we're doing for that. All right, so this is just called the torus. So the T2 here is called the torus. Okay, so again, in these spaces where we're doing a little bit of identification, especially in S1 and in the torus here, just be careful about how points look in some of these spaces. So especially in the torus here, you can't have 2 points that you would think are actually far apart, but they're actually really close together. And it's because we're gluing things together and doing some kind of identification. Okay, so for example, if you have the point, if you take the point 0.5, and 0.999. And then take the same point 0.5, the x-coordinate, and then just put a 0 right there. Just using the kind of maybe the usual distance metric that you think, and you think of those things would be kind of far away. But since we're identifying points together, especially on S1, these points may look far apart, but the actual distance between them they only have distance 0.001. That's all their distance is. So it may look like that the points are like, maybe you would guess 0.999, but again, since we're identifying 0 and 1 together, you can think of the zero on the edge there is really kind of like a 1 in there, since the 0 and the 1 are all together. So that distance is really going to be small. Okay, so that's what we'll have for there. And again, it's just from the fact that we're identifying 0 and 1 together. If we didn't have any of the identification together, those points would look far away from each other. So another view of T2 that's usually helpful is that you can take just a unit square, and if you want to visualize what's going on with that, you can just identify the edges of the unit square together and bend them together and stretch them out to get the torus and stuff. Okay, so we can also view this as a unit square with opposite sides identified or glued together. So all we're doing here is we're just taking the unit square, and the opposite sides we're really going to think of as the same, or we're going to glue them together. So you can just take these sides, and what you'll do is you just wrap it around, and whenever you identify them together, you'll just get kind of the cylinder. And then by identifying the other sides together, you can stretch it over and connect to the other side, and that's how you'll get your donut, or you'll get your torus. All right, so any questions so far? Nope. Okay, so those are just some examples that we'll be dealing with, and again with the metrics that are related to this. So let me just remind you a little bit of convergence in these spaces, as far as metric space is concerned. and give you a few results from the metric space just to keep in mind. So we'll let M be a metric space. And suppressed in that is the distance metric d. I'm not going to write the d out all the time. Okay, so we'll say a sequence xn, and go on to infinity, converges to x. If the distance from xn to x converges to 0, as n goes to infinity. Okay, and of course we'll usually write xn goes to x, or in the usual limit notation, we'll write that as well. Okay, so again, we're going to be talking about convergence of sequences in different dynamical systems. The convergence of the sequence is completely dependent on the metric. So again, you change your metric, you're going to change how your sequence converges. Okay, so for example, if you go into S1, with metric as we had right there, okay, if you actually look at the sequence n minus 1 over n, as n goes from 1 to infinity, as a regular real number sequence, this would go to 1. But since we're in the unit circle, and 1 and 0 really identified with each other, this really converges to 0 instead. Okay, so again, just be kind of careful. If there's any identification in the space here, sequences may not act as you normally would think they would act. Okay, so again, this is just a product of the fact that 1 and 0 identified with each other. So this sequence is just going to converge kind of where they meet up.
And if you had something like, say, converges to 5, is that also your conversion to 0 since it's on the integer point?
Yeah, sequence kind of converging to 5. We'll get kind of how we can deal with numbers that are maybe not in 0, 1. And whenever we talk about a map, it's going to be, if you're familiar with algebra and modular addition, there's a mod 1 out there that we'll use in these cases. That'll help us take care of points on the unit circle whenever we think of 5. So 5, you may think about just going around the circle 5 times. If you want to think of another point like that. So 5 would be kind of identified with 0. So if a sequence converged to 5, in the usual sense, and the circle would look like it converged to 0. So just to give you an easier characterization of continuity in metric spaces, so we'll say a function f from n to m between metric spaces. Say this thing is continuous if whenever we have a sequence that converges to x, then the function values f of x and converge to f of x. So kind of usual definition of continuity here. Okay? And then we'll talk about compactness. So a metric space is compact. Okay, so a lot of definitions from this with topology. Every open cover is a finite subcover. There's even an intersection property from topology that you can use to characterize compactness as well. But the one that we're going to use is, since we're talking about dynamics and we're going to talk about the sequences associated with it, we're going to think about it in terms of sequence. So a metric space is compact if for every sequence in M, so M is our metric space here, there exists a convergent subsequence. The compactness that we'll be talking about, at least for a little bit, there's two kind of theorems that are connected to that. One's way more well known, of course, than maybe the other ones if you haven't taken topology, but at least this one, if you're in a metric space, just keep these facts in mind. And we'll talk about this in the symbolic case too. So we'll have, just let M be a compact metric space. Then a set E contained in M is compact if and only if it's closed. So closed and compact metric spaces are equivalent. And then going back to the product topology that I had defined earlier in the topological sense, I'm going to define this really in the metric spaces since we're going to be kind of dealing with metric spaces all the time. Okay. But this works for any topological space, and it's known as Tikhonov's theorem. And all it says is that a product of compact spaces is also compact. But it has to be in the product topology. So you can take an uncountable product of spaces. As long as you topologize it with the product topology, it'll remain compact. So the uncountable part doesn't really matter at all. All right, any questions on that?
You mean a product of a compact metric space?
Yeah, so really this theorem works whether it's metric or not. So in this case, we're going to be dealing with metric spaces, but this works for topological space as well. So this space this could be metric, or it doesn't really matter, just any type of topological space would also be. Metric or topological works just fine.
But by your definition for a compact space, you need a like metric to describe the convergence.
Yeah, by my definition, yeah, we're going to be dealing with the metric here. This is really just like, in this case, yeah, you'd really like get from what I've said here, you would need a metric space. In general, though, the general theory of Tikhonov needs no metric, needs no metric whatsoever. You just need a topological space, and that topology gives you a compact space for that thing here. So yeah, a product of compact metric spaces is what we're going to be using in this case. But in general, this theorem works whether you're in metric or not.
You also have the notion of compactness.
Yeah, of course, yeah. That's what I'm saying. I mean, the notion of compactness that you may have done before that doesn't deal with sequences. It's just every open cover is a finite subcover, right? Yeah. Just like the usual thing. So that definition would pull through here as well. Okay. All right, any questions on that? Good. All right, so I didn't anticipate doing a review the entire time, but there it is.
But dynamics, though, right?
I know. We're going to do dynamics, man. But a lot of this stuff does depend a lot on dynamics, so I didn't want to go through. But next time I will go over a lot more examples and talk about more of the dynamics that deals with that. So, and some of this topology stuff is maybe good to see too, if you've never seen it before. So these things are really delicate to deal with in dynamics, right? Yeah, as Malcolm is raising. So, anything? Any questions?
Any questions?
When's the next one?
The next one's going to be next Monday.
Maybe
I'm
because
hoping.
next Monday is March.
It's on my birthday.
Oh, it's your birthday.
It's on my birthday.
Oh, it's your birthday.
Yeah, March 2nd's my birthday.
Let's celebrate.
So we're bringing
We'll
cake that day, or?
celebrate by making me talk.
Oh.
And bringing food.
Maybe he will this week. So, well, we're not sure about that.
Yeah, we'll see.
We'll see.
We'll see if anything is scheduled for this time. If not, then we'll definitely do it. And I'll definitely talk about more about dynamics.
All right. Okay, good. Thanks.
This is the second time I've been turned into a topology manifold stuff.
Gotcha. Gotcha.